Alright, so let's take a look at how a stationary wave actually looks like in an open pipe. So for example, this open pipe, right? So there's one opening here, there's another opening here. So this is the so-called first stationary wave that I can form in the open pipe. So how is this stationary wave formed? Very simple. So first we have an incident wave, assuming it's a sound wave. So there's an incident sound wave traveling through the first opening of the pipe. So when you reach here, apparently, right, due to the fact that there's some air pressure difference between the outside of the pipe and the inside of the pipe, right, the incident wave will get reflected off, and the incident wave and the reflected wave will superpose to form your stationary wave. So looking at this, the stationary wave, right, have a node here, and both end of the open tube must be a ND node due to the fact that you must obey the boundary condition. Okay, so looking at these, right, what should be the wavelength of this stationary wave? So this must be a half a wavelength. Why? Because from here, right, all the way to this point is 1/4 of a wavelength. From here to here is another 1/4. So you add up, right, will be half a wavelength. Okay, let's take a look at the second stationary wave, or what they call it, the second harmonic. Okay, so likewise, right, this is a second stationary wave. So there will be a ND node here, a node here, ND node here, a node here, and an ND node here. So this is one full wavelength, because from here, right, to here you can see it's a one full wavelength. Okay, now we look at the third harmonic. So this is the third harmonic. ND node here, ND node here, ND node here, and ND node here. So how many wavelengths should this be? Very simple. So from here all the way to here is one full wavelength. So from here all the way to the opening, right, is half a wavelength. So this is 1.5 wavelength. So that is how we actually calculate the wavelength in the open tube.